So we have been talking about the gas laws. Okay, and when we're talking about the gas laws, we've been uh, we've been considering the three gas laws lah. Okay, which is Boyle's law. Okay, and then there's Charles' law, and then after that there's Gay-Lussac's law. Okay, but Gay-Lussac's law is also known as the pressure law. Okay, just recap. All right. Now, all these three can be determined by the triangle of the triangle lah. Okay, P, V, and T. Remember, if they are this way, then it's directly proportional. If it is this way, then it is inversely proportional. So what you need to remember is in each of this one, Boyle's, Charles, and Gay-Lussac, okay, which is the constant variable. When you remember the constant variable, then you know how this one. So in Boyle's law, the constant variable is temperature. In Charles' law, the constant variable is pressure. So you close pressure, and then you know, okay, volume is directly proportional to temperature. And then in Gay-Lussac's law, okay, the volume is the one that is constant. Okay, and then don't forget that besides these three, in all three of the gas laws, the mass, okay, the mass astaga, the mass of gas, okay, is also another constant variable. Okay, it's also another constant variable. So when we look at this, then we want to know, okay, how is the gas laws applied? Okay, so for example, in question 1 over here, why is it that a dented ping pong ball, okay, can be repaired by placing the dented ball in hot water? Okay, name the gas law that corresponds to this situation. Okay, so dented ping pong ball. Sometimes you play ping pong and then suddenly you step on the ping pong ball, then it becomes gamete makan. But when you put it inside hot water, after a while the gamete will open itself. Okay, so first of all, let's take a look. Hot water represents which quantity? It will represent temperature. Okay, and then what about the gamete ping pong ball? Okay, are we connecting this to pressure, or are we connecting this to volume? Okay, so since the gamete ping pong ball is smaller than the open size ping pong ball, so obviously we're talking about a volume change. Temperature increase, volume will go from small until big. Okay, it will increase. So whose law is this? This is Charles' law. Okay, so temperature increases, volume of gas expands. So volume of gas increases. So the gas pressure is constant, and this will be Charles' law. That's how we will explain this. Okay, temperature increase, volume increase, gas pressure is constant. Okay, because the pressure inside the ping pong ball can't really change much lah. It's just the volume is the one that's changing. Okay, all right. Next one. Now explain why it is very dangerous to throw an empty aerosol can in fire. Okay, name the gas law involved. Explain why it is dangerous to throw an empty aerosol can in the fire. So when you're talking about fire, obviously you're talking about temperature change lah. Okay, so an empty aerosol can, empty aerosol can, probably there's no gas in there lah, so the volume is very small. Okay, but because of that, okay, whatever gas that is left in here, if we increase the temperature, it is going to increase in pressure. It obviously can't increase in volume because the aerosol can it cannot expand ma. And remember I mentioned before, the big thing that differentiates between Charles and Gay-Lussac's law is that in Gay-Lussac's law, the volume cannot expand. It is a set volume already. And volume is explained by the size of the container, by the volume of the container. If the volume of the container can expand or deflate like the volume of a balloon, then the volume can change lah. But in this case, the volume of the gas cannot change because the aerosol cannot change volume. So this has to be pressure law. Okay, when the aerosol can is heated, the temperature of the gas increases. And so the rate of collision between gas molecules with the wall container increases. So the gas pressure will increase and the aerosol can explode. That's why it's dangerous. Okay, so whenever if you have an empty aerosol can, please learn how to dispose of this in the correct manner. Never ever throw it into the fire. Otherwise it will explode. Okay, of course the explosion is not like like bomb explosion lah, but it's big lah. Okay, it's a big one because of the big gas pressure. Okay, so this is called pressure law. Okay, another name for pressure law will be Gay-Lussac's law. Okay, the third application, and this one we have explained before, explain why the size of the air bubble increases as it goes up to the surface of the water. Okay, this one I've explained before. So this is the English version. Okay, when the air bubble rises up, okay, the depth decreases, and because the depth decreases, the air pressure reduces. Okay, as the air bubble is going up, the pressure is getting smaller, and the size of the air bubble is increasing. So that means the volume is getting bigger. So whose law is this? This will be Boyle's law. Okay, when gas pressure decreases, volume of gas increases. So the size of the air bubble increases as it goes up to the surface of the water. Okay, it's an important thing. This is a very important application, one of the most important and very commonly asked is this. Okay, all right, let's go on. Okay, now next one. So a car starts a long journey from Malacca to Kedah, okay, through the North-South Highway. So when cars travel very far, okay, why does the car tire become hot after a long journey? It's because of the frictional force between the tire and the road. Okay, there's a lot of friction between the tire and the road, and after a while, not just after a while, after a short while or so, you find that the tires will get hot. Okay, next time if you go traveling somewhere, don't need maybe if you've been driving around for half an hour, once you get out of the car, you try to feel your car tire you can feel that it's actually hotter lah. Okay, and it's hotter not because of the engine become hot. Okay, it's hot becomes because there is a frictional force. Okay, the friction always causes heat. Okay, something that we will look at, especially when we go to Form 5 lah. Okay, so what will happen to the air pressure in the tire? The air pressure will increase as the temperature increases. Okay, because we know that it becomes hot. Okay, sorry, it becomes hot. Hot means temperature increase. So temperature increase can only mean two things. Either the pressure increase or the volume will increase. But in the case of a car tire, okay, we have to assume that the volume is the same lah. Okay, so the air pressure will increase. That's why let's say after a long journey, you get out of the car and you touch your car tire. When you press it, you feel that it's harder. Okay, you feel that it's harder than it usually is lah. Okay, and this is an indication to us that the air pressure in the tire is much bigger. So what is the negative impact that will probably happen? Okay, the high pressure may cause the tire to explode. Okay, and that's why it's not too good to pump your tires to the maximum pressure possible lah. It's not good lah. If you're going to travel far, you want to reduce the pressure a little bit, because after all the traveling, the car air pressure will increase. The car tire pressure will increase. So you don't want it to increase until it explodes, because the high pressure will cause the tire to explode. So what is the benefit for a driver to stop at a rest area? Besides reducing the boringness inside the car, it is also to cool down the tire, to give it some time to reduce the air pressure, so that you can travel even further lah. So don't just travel all the way. It's not good for your car tires lah. Okay, take frequent breaks. Okay, so that the driver can relax and so that the car tires also can relax. Okay, otherwise you may end up with a punctured tire because the air pressure is too high. And this happens a lot. It happens more often than you think. Okay, people will be driving, and then suddenly they'll be like, "Hey, how come my how come my tire punctured already?" Then they didn't realize that it's because they've been traveling so long that the tires become so hot, and then the pressure becomes so high that the tire just, okay lah, the tire didn't explode lah, but it just poof lah, okay. It just decided to puncture because there's too much pressure inside the inside the car tire. Okay. All right, this is the last one. Okay, explain how a bicycle pump functions. Okay, so again, we consider uh, what the two what the two quantities are. What is the quantity that is changing? Okay, obviously in this case, because there's this air over here and it is in a container, we're talking about volume. Okay, if you notice, the bicycle pump is very similar to the syringe that I showed you the other day. Okay, so we know that we're talking about volume and pressure. Okay, so this has something to do with Boyle's law. Okay, Boyle's law. So when we push the piston in, we find that the volume of the air inside is lowered. Okay, and when the volume is lowered, according to Boyle's law, the pressure will increase. Okay, the air pressure inside will increase. And so because of that, high air pressure will push the air into the tire. Okay, that's a very important thing. So we always think that it's because of our effort. We are pushing the air into the tire. Actually, it's not. Okay, the only thing that we're doing is we're just pushing the piston only. Okay, what is actually happening is Boyle's law. When we push the piston, the only thing we're doing is just reducing the air volume inside the piston. Okay, what is really pushing out this one is the high air pressure. Okay, the high air pressure is the one that pushes the air into the tire. Okay, so we have to relearn this lah. It's not like, oh, okay, I'm pumping air into the tire. Actually, it's not true. No, you are not pumping air. You are just reducing the volume inside the piston only. That's all you're doing. Okay, the thing that is pumping the air, it is the air pressure itself, because it is at a high pressure, so it needs to go somewhere. Okay, so the high air pressure is the one that pushes the air into the tire. So, so yeah, don't be so perasan. Okay, you're not the ones that are pushing the air into the tire. All right, number one, answer please.
A.
Number one is A. Why do they put this? Okay, number one is A. The mass. Okay, the the mass is the one that is not changing. Okay, no matter what happens, okay, always the mass is not changing. Okay, although this is some gas trapped in a cylinder compressed at a constant temperature, temperature is not changing. But another thing that doesn't change is the mass. Okay, number two,
D.
right? Very good. D, the average speed of the molecules increases, and this is this explains okay, the pressure. Okay, the pressure increase. Number three,
D.
D, the trapped air of the air molecules are hitting the piston more often. Let's hold on. I don't think it's D though. A. Why does the piston begin to rise when the syringe is placed in hot water? So hot water means temperature increase. Temperature increase, if the piston is rising, means it cannot be this, because the trapped air of the molecules hitting the piston more often explains pressure. But this is not talking about pressure. If this is going up, okay, when the piston begins to rise, Trevor, what is changing? It can't be pressure.
Volume.
The volume is changing. Okay, if the volume is changing, then this is not the answer lah. If the volume is changing, it will be A. Okay, the walls of the syringe are expanding. Well, technically, it's not the syringe is expanding lah. It's the piston that is expanding lah. Okay, hold on now. Let me see the trapped air molecules. Yeah, I think the difficult part about this is the word more often, because whenever we see the words more often, okay, we think about pressure, because that is the one that contributes. The hitting of the piston more often is the one that contributes to pressure. Okay, so since we're talking about volume, and I'm very glad that you got that aspect correct, lah. You know that we're talking about volume increase. We need to talk about the expansion of the piston itself, lah. Okay, actually, it's the piston that is going up, lah. Okay, the walls of the syringe is expanding as if it's going to get bigger. Okay, never mind. Thanks. Number 4. Next person.
C.
C. You sure? I don't think it's C though. Is it Yeah. Okay, let's consider this. How do you get C? Can you tell us what is your calculation like?
This one I tembak.
So you tembak. Okay, everyone. This one, first of all, we have to know whose situation are we talking about here? Boyle, Charles, or pressure? This is your question, so you have to answer every question that I'm going to ask. Whose situation are we talking about here? Is this Boyle, Charles, or Gay-Lussac's law?
Gay-Lussac.
Gay-Lussac Gay-Lussac means got change in temperature, Oh, but in this case, there is no change in temperature.
Oh, Boyle.
So it has to be Boyle's law. So Boyle's law is P1V1 equals to P2V2. Okay. Now in this case, okay, the only pressure that is affecting is the atmospheric pressure, because this one is not pushing, this one is going downwards. So we're talking about 75 times 25. Okay, 75 times 25 equals to, okay, in the second situation, the gas over here is being pushed down by the atmospheric pressure, which is 75, plus with this 5 cm of mercury. Okay, so we're talking about 75 plus 5 times V2. Okay, can you quickly calculate the V2 for me, please?
So, 23.4375.
Oh, okay, 23.4375. Okay, so the closest answer will be B lah. Okay, the closest answer will be B. So guys, take note now. Whenever you see a situation like this, okay, I think it helps to remember that this is Boyle's law lah, because there's no change in temperature. You don't see any heat being introduced. You don't see any any element of temperature increase or decrease. So definitely it's Boyle's law. But the difficult part about this is the fact that you actually haven't studied about atmospheric pressure yet. This is in Form 5. Okay, except for what you learned in Form 3 lah. Now remember that when something is placed flat, okay, so this mercury over here is not pushing against the gas. It is going downwards because of gravity. And likewise, when you put it upright like this, this one is going to go downwards because the gravity is going to pull it down with a pressure of 5 centimeter Hg. Okay, so yeah, you might want to start this question, okay, just to take note of how the working is done lah. Okay, the pressure of the water increases as the depth of the water increases. Correct. Okay, that's why the volume decreases. Okay, fine. B is correct. Okay, the pressure of the water increases as the depth of the water. The deeper you go into the water, the higher the pressure. And actually, we feel it. Okay, we feel it like if you've ever been diving, when you go very deep inside the water, you're going to feel your ears are going to start to get very pain, especially the deeper that you go. And that's because of the added pressure of the water. Okay, the deeper you go, the pressure of the water will increase. All right. Okay, number 6. Who is after Chen He? Iril. Can I have Iril for this, please? Okay, B. Let's see. Why would you get the answer B? How did you get it? Can you explain to us? First of all, Iril, tell me what law this involves. This is the most important. If you don't know what law this involves, then no matter how many times I teach also, it will not happen. You have to be able to tell me which law this is involving. Gay-Lussac. How do you know that it's Gay-Lussac? Because the temperature change with what? Okay, so the good thing is, at least okay, I'm very glad that you managed to identify that there is a temperature change. Or trapped air is heated, okay? But what is the second thing that changes? Okay, the volume. So if it is the volume change, is this Gay-Lussac's law? Really? Okay, it refers to Charles' law. So Charles' law will be V1 over T1 equals to V2 over T2. Except that the temperature, okay, which I've explained in the previous class, must be changed to Kelvin. Okay, so tell me, this 27 degrees Celsius, again, I real, is how many Kelvin? 300.15. Where do you get all this 15 from? Where do you get this 0.15? Why plus 273.15? Where did the 0.15 come from? I want to ask Irela, okay, where did they get this 273.15 from? Okay, I have a feeling that there is some truth to this 15. Okay, there is some truth to this 15, but unfortunately, okay, at our level, at our like very noob Form 4 level, okay, it's actually only plus 273. So this 27 degrees plus 273 will give you 300. Okay, the volume up here will be 10. Okay, and then they are asking what is the temperature when it is heated to 10.9. So we're talking about 10 over 300 plus 10 point, sorry, equals to 10.9 over T2. Okay, Iril, can you calculate T2 for me, please? Okay, how would I switch this around? I cross multiply. So T2 times 10 equals to 10.9 times 300. And so my T2 will be equals to 10.9 times 300 over 10. How much is this, Ariel? Okay, 327. Change it back to degrees Celsius, please. All right, 54 degrees Celsius, which is finally the correct answer. Okay, now I want to mention something. Okay, I think it's very interesting that Iril chose to add it together with 273.15. Okay, and as I said just now, it is the actual correct value. Okay, the actual absolute zero is actually 273.15. So I will have to give it up for Iril, okay, for, and I don't know whether Iril researched this or he googled this at the last minute but this is this is the actual value okay. But at Form 4 level because we are all still noobs, okay, at this physics whole thing, right, we don't really go for the 273.15 okay, we go for 273 only, okay. But it's good extra information to know that in actual fact is 273.15. Okay, the absolute zero temperature, the lowest temperature that we can achieve in our Earth, okay, is negative 273.15 degrees Celsius. Okay, but okay, for our physics purposes, kita hanya guna 273 saja. All right, question number 7. Is Diana here? Oh no. Let's look at the name list. I think 17 means she's not here. Okay, Rahman, your turn. Okay, A. How do you get A? Tell me what law this is and how did you get the A? It'll be much faster if you just unmuted yourself.
Charles law.
Charles' law. Okay, fine. This is Charles' law because temperature increase. Okay, there's a temperature increase. We want to find the final temperature. So there's a temperature increase and the volume also increase. Okay, very good. Charles' law. Okay, tell me how you got A, please. Okay. All right. The answer is D. Because, and I suspect the same thing, okay? The same thing like what I've been saying, and I have been babbling this for I don't know how many times. Charles' law, Gay-Lussac's law, you need to change the temperature, okay, to Kelvin. Okay. This is funny though. Why? Hold on. Is it really D? 3 and 3P. So this is P over 30 plus 273 equals to 3P over T2. Fine. So 303. 303 times 3 minus 273. Yeah, 636. Okay. So how do you count C though? 303 is 303 is this one, right? P over 303 equals to 3P over T2. So bring the T2 up. So T2 equals to 3P over P times 303. The P will 3 times 303 is 909 Kelvin. So 909 Kelvin minus 273, you'll get 636, which is correct. Raman is correct. How do you get C, Wong? Because 303 is just 27 plus 327, 30 plus 273. Yeah, some careless mistake. Okay, it's okay. Don't worry. This is where we learn. All right, number 8.
D.
All right, very good. D. Yeah. So this is 132 times 273. What law is involved here?
Gay-Lussac's
Yeah.
law.
Okay, it's Gay-Lussac's law because it's pressure and temperature. Okay. All right. Number 9. After Mara, after Mara is Leong Kao. Oh. Okay. C. What is happening to everybody? Okay, why is this Gay-Lussac's law? Obviously, hot air and ice will be temperature change lah. Okay? But then the bottle will kena kemek. Okay. Yeah. I think I can understand why, Leong, you would say C. Okay, you would say Gay-Lussac's law or pressure law because of the compressed this one, right? Okay, but in actual fact, it is Charles' law because the amount of gas inside the inside the bottle hasn't changed, Okay, and they are just yeah, they are slowing down, and so because of that, the volume decreases. Oh, hold on now. Yeah, I think it's very ambiguous. Like it could be B, it could be C, but I'm more inclined towards B. Okay, I think this is a better situation to explain B. Okay, because yeah, actually you're right lah. The volume doesn't change. Okay, you know what? Let me get this. Let me get back to you on this. Okay, I think it's B lah, Charles' law, but I think there is some truth to why Leong would say it's C. Okay, I'll come back to you on this. Okay, we'll explain this later. Okay, number 10. Pressure unchanged, but are you if if it's pressure unchanged, then it cannot be Gay-Lussac's law. Leong, if pressure is not changed, then it will be Charles' law because pressure is constant, pressure is unchanged. But okay, but when I think about it, it seems like it's Gay-Lussac's because if the bottle compares bahkan, it means that the pressure is less. You know what? Okay, I will come back to this. I will explain this on Monday lah. Okay. All right. Next person, Joey. Question number 10, please.
A.
All right. This is a very simple graph because we've already done this before. Number 11, Ivers. Fixed mass of gas, volume, fixed volume. Which statement is correct? A. The pressure of the gas is constant. Cannot be. It's already given to you that the volume is fixed. Means the pressure cannot be fixed. If the volume is fixed, whose law are we talking about? Think about the triangle. Okay, PVT. If the volume is fixed, this is a relationship of P and T. Whose relationship is this? Is it Boyle, Charles, or Gay-Lussac? Boyle's. Ivers, you're just stabbing in the dark, right? No, it's not Boyle's law. It is Gay-Lussac's law. Okay, now if it is Gay-Lussac's law, you're talking about temperature change, pressure change. So which of these statements, okay, tells us about pressure change. It can't be A because the pressure of the gas is constant. Definitely not A. Which one? Between B, C, and D? Please don't guess. Okay, it will be D. Okay, the molecules of the gas move with higher velocity because the higher the velocity, the more the collision with the walls, the higher the pressure. Okay, that is the sorry, that is the order in which it goes. Why cannot it be C? The kinetic energy of the gas molecules is constant, also is wrong because you're changing the temperature. The molecules of the gas move further apart only explains a volume change. Okay, because if the molecules of gas move further apart, the volume of the container changes. But in this case, the volume is fixed. Okay, a fixed volume when it is heated. All right, good. Number 12. Next person. It is Ethan. B for Charles' law.
Yeah.
Are you sure? Charles' law and Gay-Lussac's law, let's ignore this now, okay? Charles' law and Gay-Lussac's law must involve a change in temperature. In this case, we don't see any temperature being changed. It's just the piston being pushed in and after the piston pushed in. Okay? What does the Borden gauge measure? Do you remember, Ethan? What does the Borden gauge measure? Between pressure, volume, and temperature. What does the what does the Borden gauge measure?
Pressure.
Yeah. Okay, very good. It measures pressure. Okay. What about this? The size, sorry, the pushing in of the piston represents which quantity? Volume or temperature?
Volume.
Represents volume. So this is the relationship between pressure and volume, which is whose law?
Boyle's law.
It's Boyle's law. Okay, very good. All right. This is where we learn from mistakes. Okay, don't worry about this. Okay, last question. Chloe. So Bernardine, Carlson, and Elvin, you are the lucky ones today. Chloe, this is the last one for you. Which graph is correct? Okay, it will be graph D. All right, very good. Because this is in degrees Celsius. Okay, be very careful, guys. If it is a straight line directly proportional like this one should be in Kelvin.